The temperature sensors supplying input to the ECM include the coolant temperature sensor and intake manifold temperature sensor. Cummins temperature sensors utilize thermistors. A thermistor's resistance is inversely proportional to temperature. As temperature increases, resistance decreases. A working range can typically go from 500 ohms at the highest temperatures to 40 k ohms at the lowest temperatures. However, the change in resistance is not linear, nor are all thermistors the same. It is necessary to compare the values measured to published specifications to determine the appropriate repair procedures. The pressure sensors used on the engine include the intake manifold pressure sensor and ambient air pressure. In addition to these sensors, the signature engine has multiple fuel pressure sensors. Pressure sensors work by capacitance. The pressure sensor contains a disc that has the pressure to be measured on one side and atmospheric pressure on the other side. Pressure acting on the disc causes it to bend and get closer or further away from a second metal disc. As the gap changes, the capacitance also changes. An integrated circuit inside the pressure sensor converts the capacitance value into a voltage signal that is proportional to the measured pressure. A gauge pressure sensor has atmospheric pressure on one side. It is vented by a hole in the sensor or through the stranded sensor wiring. The pressure measured by these sensors depends on the atmospheric pressure, just like a mechanical pressure gauge. This type of sensor reads 0 when it is reading atmospheric pressure. An absolute pressure sensor has a near vacuum on one side. This type of sensor provides a signal representing the total actual pressure. This type of sensor reads approximately 14.7 psi or 29 inches of mercury when it is reading atmospheric pressure. Both the Signature and ISM oil systems utilize a combination pressure and temperature sensor installed in the oil rifle. Combining these two sensors into one provides for the ability to monitor temperature and pressure from the same location. In addition to the combination oil pressure temperature sensor, the Signature engine uses a combination sensor for both intake manifold pressure and intake manifold temperature. By combining pressure and temperature sensors into a combination sensor, the number of parts has been reduced. This new sensor technology also helps to improve sensor accuracy. This not only simplifies installation, it also simplifies troubleshooting and repair procedures. Speed and position sensors come in two types. The engine position sensors and vehicle speed sensors may be variable reluctance or VR sensors or Hall effect sensors. VR sensors contain a fine wire wrapped thousands of times around a magnetic core. As a piece of ferrous metal, such as a gear tooth, passes near the tip of the sensor, the magnetic field is disturbed. This causes varying voltage to be generated by the sensor. The voltage from the sensor varies with the speed of the target passing the sensor, the proximity of the target to the end of the sensor, and the strength of the magnet in the sensor. The ECM can detect this voltage and determine that a gear tooth or target has passed. For example, vehicle speed sensors generate a voltage pulse for every tooth on the tail shaft gear. Some of the engine speed and position sensors are Hall effect sensors. This type of sensor provides a digital signal rather than the analog signal provided by previous speed and position sensors. In addition to the added precision provided by this type of signal, the Hall effect sensors have been proven to be more durable. Hall effect sensors contain a piece of semiconductor material that changes conductance in the presence of metal. This is called the Hall effect. These sensors are basically proximity sensors and detect when metal is within 0.1 inch of the front of the sensor. An integrated circuit inside the sensor generates a voltage signal to show proximity. The voltage of the sensor will be high when the sensor is close to metal, and the voltage of the sensor will be low when the sensor is not close to metal. The speed of the tooth or target passing by the sensor does not affect the operation of the sensor. These sensors often use a series of targets to determine engine speed, camshaft position, or crankshaft position. Since a Hall effect sensor signal is based on proximity, this type of sensor can be installed to indicate a mechanical position. For example, a sensor installed in the transmission can provide a signal indicating transmission gear selection. Position sensors are used to supply information to the ECM about accelerator position. The accelerator pedal is located on the floor of the vehicle. This drive-by-wire pedal transmits the operator input for desired speed to the ECM and eliminates the mechanical linkages and cables connecting the foot pedal to the fuel system. The accelerator pedal is a dual-input device to the ECM. It provides both an idle-off idle signal and an accelerator pedal position. The accelerator uses a sliding contact on a conductive strip to provide a signal for idle and off-idle validation. At least one of the two switches is always closed. This is a safety redundancy check to help ensure that the accelerator pedal is not malfunctioning. The on-idle switch is a normally closed switch, indicating that the pedal position is at idle. This is the normal or foot-off position. The off-idle switch is a normally open switch. When this switch is closed, this indicates that the pedal has moved off its idle position. In the idle or no accelerator command position, the 5-volt supply is passed through the on-idle switch to the ECM, indicating accelerator idle position. When the accelerator pedal is depressed, the on-idle circuit opens and the off-idle circuit closes and sends a signal to the ECM. This is only an idle-off-idle signal. It does not indicate the amount of accelerator pedal travel. Because this idle-off-idle validation switch uses a sliding foot to send its signal, under certain circumstances, the ECM receives a signal from both switches. When the accelerator is held in a slightly depressed position, the sliding foot can contact the idle and off-idle conductive strips at the same time. If this pedal position is held, or if both signals are sent simultaneously for any reason for longer than the ignore time value programmed into the ECM, it will log an accelerator pedal fault, fault code 431. The accelerator pedal position is signaled to the ECM by the use of a potentiometer. The potentiometer has a 5-volt supply, negative return or ground, and a signal line. In the idle position, the accelerator pedal position signal to the ECM is low, typically less than 0.4 volts. As the accelerator pedal is depressed, the signal voltage to the ECM increases proportionally to the pedal travel. This continues until the pedal is fully depressed and the signal voltage is at its highest level, typically greater than 3.8 volts. The ECM uses this signal to determine the position of the accelerator pedal. The accelerator pedal position sensor and the off-idle and on-idle circuits work together. In the idle position, the on-idle switch is closed and sends a signal to the ECM, the off-idle circuit is open, and the accelerator position voltage to the ECM is low. As the accelerator pedal is depressed, the on-idle switch opens and stops sending a signal to the ECM, and the off-idle switch closes, sending a signal to the ECM, indicating that the pedal is no longer in its idle position. At the same time, the accelerator position voltage increases. As the pedal is further depressed, the off-idle validation signal remains, and the accelerator pedal position signal continues to increase. Until the ECM receives this off-idle signal, it ignores any signal it receives from the throttle pedal position sensor. This eliminates engine speed changes due to foot pedal position sensor errors and provides a margin of safety from a failed accelerator pedal. The fluid level sensors provide information about coolant level in the top tank of the radiator, oil level in the Sentinel makeup tank, and water level in the fuel filter. The coolant level sensor, installed in the top tank of the radiator, sends a signal to the ECM when the coolant level in the top tank drops below the sensor. If the engine is equipped with the Sentinel Advanced Oil Maintenance System and the makeup tank, the oil level sensor installed in the makeup tank sends a signal to the ECM when the oil level in the makeup tank drops below the sensor. This sensor has a floating ring around the sensor shaft. When the oil level is above the sensor, the ring floats, and the magnet in the ring causes a set of small contacts in the body of the sensor to open. However, when the oil level drops below the sensor, the magnet in the ring moves away from the body of the sensor, allowing the contacts to close. This sends a signal to the ECM that the oil level in the makeup tank is below the desired level. The water-in-fuel, or WIF sensor, installed in the bottom of the fuel filter, detects the water level in the fuel filter. The water-in-fuel sensor consists of two electrical probes that extend into the chamber at the bottom of the fuel filter. These probes measure the conductivity of the liquid in the filter. As fuel passes through the special fuel filter, water settles in the bottom of the filter. When enough water collects in this area, the conductivity measured by the water-in-fuel sensor increases beyond a threshold value. After a short time delay to prevent false triggering, a fault code becomes active and the maintenance lamp lights. This provides a real-time feedback signal to drain the water from the filter. The engine brake, manual fan, and remote accelerator on-off switches activate or deactivate the associated component. When the engine is operating at idle, this switch can be used to increase or decrease the reference idle speed. When operating in cruise control mode, this switch is used to set the cruise control to the set or resume speed and to accelerate or coast to the desired speed. For example, to increase the speed by 2 miles per hour, bump the set resume switch briefly to the accelerate position twice. To decrease the speed by 2 miles per hour, bump the switch to the coast position twice. When the cruise control switch is in the off position, the set resume switch can be used to adjust the maximum vehicle speed below the maximum vehicle speed parameter set in Insight. When in PTO, this switch is used to set the PTO speed to the set or resume speed and to increase or decrease to a desired speed. When in diagnostic mode, the key switch on and the engine not running, the fault lamps will flash active fault codes. This switch is used to advance to the next step fault code or return to the previous fault code. The PTO additional speed switch is used to signal the engine to operate at a third PTO speed that is available in addition to the set and resume engine speeds. This switch connects to both pin 14 and pin 24. When the switch is closed, the ECM receives a signal on both the pin used for the set speed and the pin used for the resume speed at the same time. When cruise control is enabled and the vehicle is moving at 30 miles per hour or greater, moving the cruise control or PTO on-off switch to the on position activates cruise control mode of operation. If the vehicle is not moving or moving at less than the cruise control minimum speed and not faster than the PTO maximum vehicle speed, toggling the switch to the on position activates PTO mode of operation. The maximum operating speed switch, if installed, allows the operator to limit the engine speed to a value set in Insight. This feature is used in situations where high engine speeds might damage vehicle components. Switches are installed in the cab or vehicle to automatically activate during specific conditions. For example, both the brake and clutch switches open a circuit when the pedals are depressed to allow the ECM to determine pedal position. The diagnostic switch is used to flash out the fault codes. Placing the switch in the on position initiates the fault lamp sequencing to flash any active logged fault codes. The engine brake selector switch supplies a signal to determine the desired engine braking level. ISM engines have 2 brake assemblies. This switch selects whether one or both of the engine brakes activate to slow the vehicle when braking is required. On signature engines, this switch selects between 6 levels of engine braking. The 3 brake solenoids on signature allow engine brake activation for one cylinder up through all 6 cylinders. A signal from the ECM to one of the solenoids activates braking for one cylinder. A signal from the ECM to the second solenoid activates engine braking for 2 cylinders. A signal from the ECM to the third solenoid activates engine braking for 3 cylinders. To activate engine braking with 4 cylinders, the ECM sends a signal to both the solenoid controlling braking for 3 cylinders and the solenoid controlling braking for 1 cylinder. To activate engine braking with 5 cylinders, the ECM sends a signal to both the solenoid controlling braking for 3 cylinders and the solenoid controlling braking for 2 cylinders. To activate engine braking with all 6 cylinders,